Welcome. In this session in linear data analysis, we'll explore a hypercube by examining the number of vertices and the number of ways that we can label the vertices. So a hypercube, suppose it has n dimensions, and let's count how many vertices we have. Well, if we're n equals 0, a point, there's only one vertex. If there's n equal 2, that's a line segment, and there are two vertices. If it's n equals 2, we're in 2D, and that means we have a square, and there are 4 vertices. Similarly, by the time we get up to n equals 3, for a cube we get 8. For a tesseract, there are 16, and so on. So what we have in general is that for n dimensions, a hypercube has 2 to the n vertices. And that means that the number of vertices of a hypercube is exponential in the number of dimensions of the hypercube. So that is an immediate problem, is when we're facing exponential growth, we know as data scientists that we're going to be having a difficult time. Now, how many ways are there to label a hypercube? Well, that depends on how many labels you have. Suppose that we have a color, for example, and we have 2 colors for each vertex. So there's 2 ways to color a point, and there are 4 ways to color the 2 vertices of a line segment, and there are 16 ways to color the 4 vertices of a square, and there are 256 ways to color the vertices of a cube. So what we're seeing is that there are 2 to the 2 to the n ways to color the vertices, and this is because for each number of vertices, for each vertex, there are 2 ways to color it. And so if we have 2 to the n vertices, that means we have 2 times 2 times 2, so that's 2 to the 2 to the n ways that we can color the vertices of a hypercube. And this means that the number of labels in our data, if our data are a really simple object, which is a hypercube, that means that we're facing super exponential growth in the number of labels when we only have 2 ways to color the vertices of the hypercube. So, in data science, there's something that's called the rule of 10. I personally am a little suspicious of it, but you'll find this in many, many sources. And that is, for every variable in your data, you need 10 samples, and some authors will say you need 20 samples. Well, let's see, between 10 and 20, what's a nice convenient number? I'd say, let's say 16, because it's a power of 2. Now, let's work out this given what we already know about a hypercube. So if you have n dimensions, that hypercube has 2 to the n vertices, and what a data scientist would ordinarily say is you need 2 to the 4th times n. Okay, so let's work this out for an example, right? And then if we're talking about the ways that we can label, then we would be sampling 2 to the 4th times n out of this super exponential. Okay, let's just work this out. Suppose we only have 4 dimensions, so that's a very small number of variables. If we're sampling 2 to the 4th times 4, that means we're sampling 2 to the 6th. So if we're sampling 2 to the 6th, which is 32, and we have 16 vertices, that's looking pretty good, right? And on the other hand, suppose that we have we're looking for labels, and we're trying to figure out what are the labels, and that's the problem that we face in clustering or in binary classification. So now we have 2 to the 6th labels, 2 to the 6th data, and we have 2 to the 16th possible ways that those data could be labeled. This does not look very good. So this rule of 10 is something that people will often use, and if we're looking at linear regression, there are good reasons why 10 times the number of variable empirically will work out very well. But when we turn to binary classification, this rule of 10 seems to break down. What I can summarize this as is this is the learning version of the curse of dimensionality.